I'm Takahiro Maeda from Toyota Technological Institute, Japan. Today I will present our research, data augmentation for human motion prediction. Human motion prediction aims at generating future motion based on observed past motion. It takes a sequence of skeletons until time t as input and predict future frames of skeletons from t+1. Human motion prediction is applicable to many applications such as collaborative robot and VR/AR applications. In such applications, robots and virtual characters can dynamically interact with people based on predicted motions. In spite of the potential applications, currently possible applications are limited because of insufficient motion data for training. This insufficiency is due to high data acquisition cost. Data augmentation is commonly used. For image-related tasks, we can easily generate diverse realistic data just by simple geometric and photometric deformations, such as rotation and contrast change. However, for motion data augmentation, such simple geometric deformations may generate unrealistic motion, as shown here. Thus, we have to maintain another property named physical plausibility, as well as diversity. A previous method failed to address both of diversity and physical plausibility. This method proposed adding Gaussian noise to joint angles. However, this resulted in a trade-off between two characteristics. To achieve both characteristics, we propose the combination of motion synthesis for diversity and motion correction for. First of all, the motion synthesis part consists of variational autoencoder and inverse kinematics. Let me elaborate our BAE. BAE trained by various motions can generate new motions and are applicable to augmentation. But we found synthesized motions are temporarily over-smoothed when applying vanilla VAE trained with insufficient motion data. These over-smooth samples lack diversity. If we train VAE with enough data, the accumulated distribution of encoded data matches the prior distribution. However, with insufficient data, the accumulated distribution gets narrower and unlearned regions appear. We experimentally confirmed that samples from unlearned region produce over-smoothed and non-diverse motions. For this problem, we propose to sample only Z bar, which is located in learned regions. This encourages motion diversity even with insufficient data. We compare motions generated by vanilla VAE and VAE with our sampling method. As we can see, our method can produce more realistic and diverse motions. Next, let me elaborate our IK motion synthesis. IK can modify the posture so that a specified body key point reaches a target position defined by a user. However, it takes huge cost to manually annotate IK target positions to all frames in all training sequences. For avoiding this huge annotation cost, we propose IK with minimal annotations by only defining a joint reachable space. First, we define a joint reachable space on each action class in its keyframe. The keyframe might be defined so that the joint reaches the farthest position. This figure shows an example of the reachable space in a key class. From this space, we sample IK target position. Finally, in order to determine the IK target positions in all frames, we propagate a positional difference from a joint position to an IK target position of the keyframe in linearly decreasing manner. From this original motion, IK can synthesize diverse motions. This is a summary of our BAE and IK. The body deformation by BAE is relatively low because BAE synthesis is based on insufficient training data. However, BAE can change the whole body posture. In contrast, the body deformation by IK can be high because IK target positions are arbitrarily given by a user, but only a part of body is changed. While each method produces diverse motions, we propose to use both of them for complementary augmentation. Next, let me explain about our motion correction. Even though diverse motions are synthesized, we empirically observed some physically implausible motions. For example, by BAE synthesis, foot skate motions are observed. By IK synthesis, limb penetrations are observed. We propose to collect such motions by forcing each motion to the laws of physics by using imitation learning in a physics simulator. In previous method, not for motion correction but for motion generation, this imitation is achieved by reinforcement learning as shown here. Based on past postures, this physics simulator output the next posture of a character X char. This X char might be different from a reference motion X left that is imitated by imitation learning. In our case, this reference motion is synthesized motions by our BAE and IK-based method. In accordance with X char and X left, this policy network output talks. The policy network is trained to minimize the difference between X char and X ref, but it is impossible to completely imitate the reference motion only by the torque given to body joint due to physical constraint. So, an additional external force is used to move the character similarly to the reference motion. As I told you, this imitation learning is proposed for new motion generation. On the other hand, our method employs this imitation learning for correcting the synthesized motion based on physical constraints. However, the convergence of this imitation learning takes several days for one motion sequence. It is not practical for data augmentation. To reduce the training time, we replace the additional force by forces calculated with running free PD controller. This is because the training of additional force is dominant in the whole training cost. This graph shows the learning progress. As the learning progresses, this value gets larger. As you see, we can reduce the training time to 1/5. We evaluate our data augmentation method based on errors in human motion prediction task. We use HDM05 dataset. As a human motion prediction method, this SOTA model is used. This table shows the prediction error on different time steps with each data augmentation. Prediction models are trained with various augmentation, namely data with no augmentation, data with noise given by the previous method, and several combinations of our method. In all cases, the error is greatly reduced by the combination of BAE and IK augmentation. However, motion correction fails to reduce error further. Motion correction weakens the data augmentation due to the imitation failure on fine footworks. This example shows that failure on tiptoeing. These motions are automatically removed from training by similarity thresholding. However, the most of corrected motions are realistic and diverse as shown here. Therefore, the motion correction is still applicable to synthesizing physically realistic diverse animations and VR applications. Let me conclude my talks as follows. Our future works include the imitation learning, robust footworks, and better combination of other motion synthesis methods. That's all. Thank you.